All right, another example of complete factorization, and this is how we can use it to solve a real-world problem. The width of a box is 2 inches less than its length. The height is 8 inches greater than the length. The box has a volume of 96 inches cubed. What are the dimensions of the box? A lot of stuff going on here. Let's start off by letting length equal L. So since the width is 2 inches less than the length, then that would be L minus 2. And since the height is 8 inches greater than the length, it would be L plus 8. And the volume is length times width times height for a rectangular prism. They also tell us that the volume is 96. So 96 is the length times the width times the height. Well, the length is L, the width is L minus 2, and the height is L plus 8. Let's pause for a second. Again, volume is length times width times height. I know the volume is 96. I know that the length is L. We assigned L minus 2 to be the width, and we assigned L plus 8 to be the height. Okay, so I'm going to simplify the right side of this equation. I'm going to start off by multiplying these two binomials, which we learned in an earlier section of the chapter. L times L is L squared. Negative 2 times 8 is negative 16. And in the middle, I kind of skipped a step here, but we have 8L minus 2L. 8L minus 2L is 6L. Okay, I'm still not done simplifying this. I'm going to distribute this L through. That'll give me L cubed plus 6L squared minus 16L. And then I'm also going to put it in standard form by subtracting 96 from both sides. I've run out of room, so I'm going to come up here. Subtract 96 from both sides, and we get this lovely looking 4-term polynomial. 4 terms, if I want to factor this, I am going to group it. So I group the first 2 terms together and group the second 2 terms together. Remember, I'm going to put that negative sign in the second group. This should look familiar. Again, like one of those intermediate steps of the AC method. Hopefully we're good at that. So I'm going to factor out a greatest common factor of the first term, and I'm going to factor out a greatest common factor of the second term. Take L squared out of the first one. And I'm going to take negative 16 out of the second one. Okay. So, first factor is L plus 6. The second factor is L squared minus 16. Hopefully you're recognizing that this second factor is not completely factored. That's the difference of squares. So, another step. There's our L plus 6. But L squared minus 16 is L plus 4 times L minus 4. Okay. Now I'll use the zero product property to solve this. Get 3 solutions. Negative 6, negative 4, and positive 4. Can you have negative lengths of a box? No, so I'm ignoring those negative answers. We only get one answer that makes sense for the length, and that is 4 inches. I'm sorry. Yeah, it should be inches. I wrote centimeters. But using that length that we just figured out of 4, I can plug in 4 into these other 2 expressions. 4 minus 2 is 2, so the width is 2 inches. And 4 plus 8 is 12, so the height is 12 inches. So there's the 3 dimensions that we're looking for. Two more equations we're going to solve. It's not pretty, but we can make it a little bit easier to look at by dividing both sides by, how about negative 6? Divide both sides by negative 6. Okay, negative 60 divided by negative 6 is 10. 114 divided by negative 6 is negative 19. Negative 36 divided by negative 6 is 6. 0 divided by negative 6 is 0. You can only do this step in an equation when you're doing the same thing to both sides. Okay, now I'm going to factor out the greatest common factor, which is x squared. Okay, as soon as I see this x out here, hopefully you guys realize that 0 is one of the solutions. Okay, if there's an x squared out here, then 0 squared is 0, and 0 times no matter what this is going to equal 0. So 0 is one of the solutions using the zero product property. As far as the other solutions, it would be values of x that make this 0. Well, that may or may not be factorable. I could check the discriminant to see if it's factorable, but to be quite honest with you, since the lead coefficient is not 1, I'm not even going to try and factor this. I'm just going to go old-fashioned, old school. Let's go back to chapter 9. Let's use the quadratic formula. Quadratic formula is just as good as factoring for finding solutions to quadratic equations, with which 10x squared minus 19x plus 6 is. It's a quadratic function. All right, so there's the quadratic formula. I've substituted everything in. B is negative 19. B is negative 19. A is 10. C is 6. A is 10. Let's simplify this. The opposite of 19 is 19. Negative 19 squared is 361. Negative 4 times 10 times 6 is negative 240, and 2 times 10 is 20. Keep simplifying. 361 minus 240 is 121. 121 is a perfect square. It's 11. 19 plus or minus 11 over 20. 19 plus 11 is 30. 19 minus 11 is 8. There's our two solutions. 30 over 20 is 3/2, and 8 over 20 is 2/5. So remember, we had 0 as one of our solutions. Don't forget about that. 3/2 is another solution, and 2/5. The fact that these came out rational answers means that this expression was factorable. But boy, it would have taken me a while. I would have to do the AC method to factor that. Forget it. I'm not interested. I'll just use the quadratic formula. It's still a fine way to get an answer. Let's do this one more time. Got this rather ugly equation, but I noticed that the first 3 terms, or all 3 terms, are divisible by 4. So let's divide them all by 4. Then I noticed that all 3 terms are divisible by x, so let's factor out x. Okay, as soon as I do that, when I've got x outside these parentheses, zero product property tells me that if this times this equals 0, then one of these has got to be 0. So x equals 0 is a possible solution. Now, as far as getting the other solutions from here, I could use the AC method to factor this. But I'm not going to bother. I just don't like it. When the lead coefficient is not 1, I would rather use the quadratic formula. Who would have thought a chapter ago that we'd actually prefer the quadratic formula as a method for solving? But factoring can be a lot easier. But when the lead coefficient is 1 and it's not a perfect product pattern or special product pattern, I'm just going to use the quadratic formula. B is negative 11. B is negative 11. A is 3. C is 4. A is 3. Let's simplify this. The opposite of negative 11 is 11. 11 squared is 121. 4 times 3 times 4 is 48. And 2 times 3 is 6. Let's subtract. Okay. Well, last time we had 121 inside the radical, but this time it's not a perfect square. Furthermore, 73 is not even divisible by a perfect square. We cannot simplify that radical. So those are your other 2 answers. Remember, we got 0 as one answer, and the other answers are 11 plus the square root of 73 over 6 and 11 minus the square root of 73 over 6. Those are our three solutions. We could turn this into a decimal. And then, well, it's actually two decimals, and we could check it by graphing this and seeing where it crosses the x-axis. Perhaps we'll do that in class tomorrow, but I think we've had enough examples for tonight. If you need to watch any of this again, I would encourage you to do so. As always, I would definitely encourage you to read the examples that are in your textbook that kind of go along with these examples, but they're slightly different. So, big time summary of complete factorization today. Back there on your first section of your notes, this is the bottom line here. All right. Good luck.